Okay, so continuity over an interval, we're going to have, our reasoning for something being continuous on an interval is almost going to sound dumb whenever I say it out loud. A function is continuous on an interval if the function is continuous at each point in the interval. Right? So, a function has to be continuous everywhere in that whole entire interval in order to be continuous on that interval. It would kind of like be if we said the whole class made A's on the test. Well, for that to be true, every person in the class would have to make an A on the test, right? One person that didn't makes that statement false. Whenever we are proving this, you can't so much prove it. Not in the same way that we can prove continuity at a point. At a point, we just got to show the limit exists, the function exists, and that those two things are equal to each other. It is not possible for us to do that for every point in an interval, because any interval has infinite points, right? Even if it is from 0 to 1, 0 to 1 has an infinite number of points, because we got, 0.5 and 0.7 and 0.721 and 0.9 and 0.99 and 0.9999. Like you have infinite points even within a closed interval. So what we're going to be doing here is more disproving a statement than we are proving a statement, because we can't actually test every single point. We can use the information that the following functions are continuous on all points in their domains. Here's my pen. Okay, so these are all different types of functions that you have looked at before in prior classes. Polynomials would be something like f of x equals x to the third minus 2x plus 1. You could also call that particular one a cubic, but this would include quadratics, lines, any something to the 4th, 5th, 6th, 7th power. Those would all be considered polynomials. An exponential is going to be something where your variable is in the exponent. So like a simple example there would be like 2 to the x, or e to the x is another one we see a lot. So we've looked at those a lot in Math 3 and Pre-Cal. Rational means that you've got to have a variable in the denominator of a fraction. So the most simple one you could have would be like 1 over x, but it could be much more complicated than that. It could be x plus 2 over x squared minus 3x plus 4, something like that. Radical, the ones that we're going to look at the most are going to be square roots. It could include cube roots, 4th roots, 5th roots, and you may occasionally see them, but square roots are going to be the primary ones that we see. Logarithmic or logs, so it might be, log base 2 of 7, or the one that we see the most often in this class is natural log of x. That's what we see most often. And then trig includes your sine, cosine, tangent, secant, cosecant, cotangent, any of those. Now, what I have here does not tell you that these functions are continuous everywhere. They are continuous for all the points in their domain. So they're continuous everywhere except for certain places. So let's look at the domains of all of these, because those are going to be important for us to know. Polynomials, you're always going to get all real numbers. Okay, so any just straight polynomial is going to be all real numbers. Same for an exponential. Exponentials, you can plug any number into that exponent. It should still be fine. You might have an exception if you get something really crazy like e to the square root of x or something like that. But in that case, it wouldn't really fit in this category because it's exponential and a radical at the same time. So you could run into something crazy like that, but most of the time you do not unless it's calculator active problem. For rational functions, the denominator is not equal to 0. So it's going to be continuous everywhere except for where the denominator is equal to 0, or the denominator cannot be equal to 0. Okay? For a radical, first of all, it only applies to even roots when we're talking about this, because cube roots, fifth roots, odd numbered roots would be all real numbers for those. So we might even want to put odd roots would be all real numbers for that. For even roots, though, I'm going to use a fancy word here, the radicand. Okay, radicand means the stuff under the square root, right? The stuff inside of the square root is greater than or equal to 0. So whatever is inside of your square root has to be greater than or equal to 0. That is because we cannot have negatives underneath the square roots. Those give us imaginary numbers. Okay, I'm going to throw another fancy word at you here so that whenever you go to college and you have PhD professors, you can be throwing things like radicand and this word out there, and then you'll sound super smart. The logarithmic function, what's inside of a log is called the argument. Don't know why, but it is. I looked it up to make sure because I was afraid I had forgotten. But the argument is greater than 0. You do not want to equal to here. Whatever is inside of a log has to be positive. Can't be equal to 0. Okay, and then for the trig functions, the ones we see the most are sine and cosine functions, and those are going to always be all real numbers. The other ones you don't see very often, but they do have vertical asymptotes. For tangent and secant, it's going to be everywhere that the denominator is 0. So this is where, I'm going to put right here, where cosine of x equals 0, and that happens, the first place that happens is at pi over 2, and then 3 pi over 2, and 5 pi over 2, and so on. So it happens at pi over 2 plus pi times k, so all of those are separated out by increment of pi. And then cotangent and secant are going to have vertical asymptotes where sine of x equals 0. And that happens at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. So any increment of pi, which can be written like this, where you got pi times k, where k is an integer. We did a little bit of that in pre-cal. There. So these are things we're looking out for. If they are asking us about where a polynomial is continuous, it's going to be continuous everywhere it exists, right? Exponential is the same. Because of that, we don't see them very often. They don't ask us about the easy questions that much. Other things we're going to be looking out for are denominators equal to 0, square roots have to be greater than or equal to 0, logs have to be greater than 0, and these trig functions. We're going to see that a lot. And I didn't put this on here because it's kind of self-explanatory. Piecewise functions are going to be a big one that show up here as well, because piecewise functions don't always meet up. So that we'll be looking out for. Is f of x equal to 1 over x minus 1 continuous on the interval? Justify your answer. So this is a rational function. It does have a discontinuity. Where is the discontinuity for this function? Is it x equals 1, right? So I have a discontinuity at x equals 1. But they're only asking me about 2 to infinity. So is this function going to be continuous from 2 to infinity? Yes, because that does not include x equals 1. So you may or may not, I feel like you're not going to see this on the real free response section very often. It is more often going to be on a multiple choice version. There's a chance on this first test, maybe, because I'm having to like put all I know about limits out there for you. So maybe, but usually not on the actual AP exam. So I would say f is a rational function and therefore continuous everywhere except x equals 1. Since x equals 1 is not on the interval to infinity, f is continuous. On 2 to infinity. It would be assumed that you know rational functions are continuous everywhere except for where their denominator is equal to 0. You are showing that here, and then showing that this continuity is not in your interval that you're looking at. So you would have a function that is continuous. Questions on those? You're not going to go through the 3-step process for proving something continuous because it's not asking you about that at a point. And you do not necessarily need to like go into greater detail about why it's discontinuous or anything there. All right, so I have a graph here. It's made up of a line segment, a point, and a part of a parabola. And A says, is g of x continuous on the interval from 4 to 8? This is an example of something that you might get sort of as a multiple choice question. They'll ask it a little bit differently if they do that. And we'll see some on the assignment tonight. So from 4 to 8, is g of x continuous? It is, because 4 is right here. And 8 is over here. And between those two pieces, my function is a solid line the whole time. So I would say, yes, it is continuous. However, if they ask us, is g continuous from -2 to 8? -2 is over here. 8 is still right over here. Is G continuous on that interval? That is a no. Why? Because there is a hole. You can use the phrase hole, that is fine. Know that if this were like a multiple choice question where it had reasoning, they might call it a removable discontinuity, but you could use either phrase. So there is a hole at, where's my hole at? X equals 3. And 3 is on that interval. Okay. Good there? You probably need to justify. Definitely on this one, I probably should add in justify your answer here. So we are supposed to decide if f of g of x is continuous for all real numbers. Now I'm feeling like the answer's probably no here because I have a denominator and I have a square root, and those cause problems. So I feel like there's going to be an issue there, right? But I need to give a reason for that. In most cases, you're probably not going to see this as a multiple choice without any explanation. You might see a multiple choice where it says yes for part A, and then for B, C, and D, they all say no, but they all have different reasons for why. So that might show up. Or it could be where it says justify your answer for that. So if I find f of g of x, that means I'm taking g and I'm plugging it in right here for x. So that's going to look like this. 1 over the square root of x plus 2 minus 5. Mm-hmm.
Rational, the denominator is not equal to 0. Is that saying that it's continuous when it's not equal to 0?
Correct. Continuous whenever it's not equal to 0. We don't really have to do a limit right here because it's saying, is this continuous for all real numbers? One point where it's not continuous, any point where it's not continuous will let us answer no for this. So there are several different things that you can do for this. I would go with what would make this 0. Your denominator equal to 0, right? Because if your denominator is equal to 0, then you have a vertical asymptote or a hole at that point, and it's not going to be continuous. There are some other options for this as well. What I would do is I would do square root of x plus 2 minus 5 equals 0. I'd add the 5 over, so square root of x plus 2 would equal 5. I would square both sides. X plus 2 is going to equal 25. And then I would subtract that 2. So x equals 23. And then I would say no, because f of g of 23 is undefined. Because at that point, you're going to get 1 over 0.
So you like set the bottom equal to 0?
Yeah, or if you use the not equal, like saying that it can't equal 0, that's fine too. But in this case, because I've got a fraction, anytime you have a fraction, the denominator cannot be equal to 0. If the denominator equals 0, you have a discontinuity, and all we really need is a single discontinuity to disprove this. You also have a square root in this one, so another option is that we can't have negatives underneath that square root either. So, or we could say that x plus 2 has to be greater than or equal to 0. So x has to be greater than or equal to negative 2. So another option is we could say no, because I'd actually probably word it this way: any number less than negative 2 gives a negative under the square root. So there's another option there. So some of these, it doesn't necessarily have to be one thing for that. Yeah. Right, you only have, so what I've got in red by itself would be plenty, or what I've got in blue by itself would be plenty. You don't have to have both of them for that, if the question is asked this way. Here. What's going to actually happen here is that, like, if you're asked to give, like, where it is continuous, it's everywhere that's greater than or equal to negative 2 except at 23. Because at 23 you get a 0 in the denominator also. So, like, your domain here would be x is greater than or equal to negative 2 except for at 23. But in this case, they're just asking you if it's continuous everywhere. Okay. This function asks you to describe the intervals on which the function is continuous. So it's very similar to the last question, but this one we do need to know every single place that we have a discontinuity. So in this particular case, I need to know, I know I have a discontinuity here, but I need to know where that's at, because if I think about x squared minus 9 over 3, I could factor it x minus 3, x plus 3 over 3, or x minus 3, right? What type of discontinuity do I have at 3? I've got a hole, because these two right here cancel out. So if I have a hole, and then I have a closed circle that fills it in, it's actually continuous, right? Mm-hmm. The first part definitely has a hole. What we've got to check for is does the closed circle, because whenever we got 3, 3, that's basically just like a closed circle, right? If it fills in the hole, then it's actually continuous everywhere. Mm-hmm.
So, like, how do you have, like, a hole and then just a building circle?
So what happens here, so when we're thinking about, in fact, let me type this into Desmos. When we're thinking about what this looks like, we could think about what it looks like when you type it into Desmos. To type in a piecewise function, I'm going to do like this: f of x equals squiggly equal sign, and I'm going to say, oh gosh, will it let me do that? I might not be able to do it actually. Does it let me do does not equal? I don't think it does. Okay, I'm going to have to do it this way, because Desmos will be, I'm going to have to say x is less than 3, and then I'll have x to the second minus 9 over x minus 3. And then I'll have, see if it'll even, I may have this wrong, x equals 3, 3. And then x is greater than 3. And the function again. In fact, let me not use the actual piecewise function. Let me just do this. I'm going to just type in x squared minus 9 over x minus 3. It looks like a line, right? But this is going to be everywhere except for 3. If I go to 3 right here on this graph, right there's my hole in the graph, right? So if I drag this over here, there's a hole at that graph. If I do g of x, I'm going to use a different letter so it doesn't confuse Desmos, equals 3, and then I put a squiggly sign, x equals 3. Let's see if that'll work. Well, I was hoping Desmos would help me out a little bit better here. You're going to have to recognize, whenever I have just x equals 3, that is the point my x-coordinate is 3, my y-coordinate is also 3. Right? So what is happening here, if I look at this graph, the top part of the function has a hole. The bottom part of the function is just a single dot. Does my dot fill in my hole right here? It does not. So this has a hole in the graph. It's not continuous. There. Now let's talk about how I can show that without the graph, right? Because this will probably be a calculator inactive problem. So in this case right here, at that hole, what's the y-coordinate look like it is? Looks like it's 6. So if instead of 3 right here, we had 6 as the y-coordinate, now that green dot is right there where my hole is at. So I've got a hole, but the dot is filling in the hole. So that would make it a continuous function. But that is not what we have right here. We've got 3, 3 for this. So, now on paper, without a graph, how can I show the hole is at a different spot than the dot for this? What can we do to find like that y-coordinate of the hole? On that graph, as you get, oh, that's the wrong graph. Let's get rid of that one. On that graph, as you get closer and closer and closer to 3, you are approaching the hole right here, right? And from the right side, same thing. You're approaching that hole. You're getting closer and closer and closer to it. What do we use for that? We use a limit, right? So what we can do is we can say that the limit as x approaches 3, we can do both sides at the same time because it's not like a less than 3 or greater than 3 right here, would be, these will cancel, and we will get 3 plus 3 whenever we plug in the 3, which gives us 6. However, if I do f of 3, what do I get? 3. So my limit does not equal my value at that case, at that point. So it's going to be continuous. It's not going to be continuous at 3. Now, this is a rational function. It is continuous everywhere else, right? So if I'm asked to tell where this function is continuous, it would be negative infinity to 3, parentheses, not a bracket because we're not including it, and then 3 to infinity. I could do it that way. You also might see it written this way, x is less than 3, or x is greater than 3. Or the easiest way is just at x does not equal 3. All x's where x is not equal 3. So f is continuous at pick one of those three expressions. That probably is going to be multiple choice, and it's probably going to have one of the three for that. Okay, so if you see one of these where it's like x does not equal, you probably need to do the limit at that point to see what it is. There's probably something going on like a hole there, and then you want to see if that dot fills it in. If we had got 6 right here, like if we got 6 in both places or 3 in both places, then it'd be continuous everywhere. We'd just say negative infinity to infinity or all real numbers for that. All right, let's look at this one. This one's a little fuzzy up here, but it's super big. All right, so we are supposed to tell the intervals where this is continuous, which basically means we need to find all the discontinuities. You're not going to see this on a free response question, not one this big. It's going to be multiple choice, so you don't have to go through all the formal limit notations for proving discontinuities here. We're going to do the shortcut method, right? So if I look at e to the x, I want to think within each piece, is it continuous? Is e to the x continuous everywhere? That's an exponential. What did it tell us for the domain? That's all real numbers. It's continuous everywhere. What about x cubed plus 2x? Polynomial, continuous everywhere. What about 5x over x minus 2? X cannot equal 2. Is that in the domain that they've given us? It is. So I'm going to make myself a note. X cannot equal 2. I need to leave that out. And then I've got cosine. Is it continuous everywhere? It is. And putting the 3 there doesn't change it. Cosine is just the wave. It keeps on going forever. So you want to check within each section first for that. But then, this is a piecewise function, so what else do you have to check? You got to check where they meet. So, first I'm going to check -1. Right? I've got e to the -1 right here, and then I'll have, that's supposed to equal -1 cubed plus 2 times -1. E to the -1, it's 1 over e. E is like 2.718. I'm not feeling like these are going to match, right? And then here, I'm going to get -1 minus 2. So I'll get -3. Are those equal to each other? They are not. I don't really know what 1 over e is, but I know it's not -3. So x cannot equal -1. You've got to jump in the graph there. We'll switch colors over here. I now need to check 0. That's a point where these need to come together. So if I do 0 cubed plus 2 times 0, I'll get 0. If I do 5 times 0 over 0 minus 2, I will get 0 over -2. What is 0 over -2? It is 0. There. Are those equal to each other? Yes, one of them has an or equal to sign, the other does not. So you got a situation where one of them ends in an open circle, but the closed circle of the next one fills it in. So we're continuous at 0. 0 is fine. And then the last thing we need to check is 4. So for 4, I would do 5 times 4 over 4 minus 2, which will give me 20 over 2, which is 10. And then I've got cosine of 3 times 4, which is cosine of 12. I don't know cosine of 12. If you think about the unit circle, like 2 pi is 6.28, right? Pi is 3.14, so you'd have to go around the circle like almost 2 times. Is it going to equal 10? No, it can't equal 10 because what's the biggest cosine can ever be? 1. What's the lowest it can ever be? -1. So I don't know what that is, but I know it does not equal 10. So x also cannot equal 10. I'm sorry, it will be x cannot equal 4. Thank you. Use your x coordinate, not your y coordinate there. All right, so if we do this in interval notation, you would do -infinity up to -1, do the lowest number first, then -1 to 2, and then 2 to 4, and then 4 to infinity. Sometimes you may just see it as a list of cannot equals. That's easier to do, but you just want to like list each section, make sure you're using parentheses so those values are not included. Okay, questions there? Okay, we got a little bit of time to get started on your assignment. It is also on